motion of a charged particle inside an electric field. Now, in chapter 1, we have studied about charges and electric field. We know that if charge is inside an electric field, then the charge will experience a force. So here also, if we have a positively charged particle, Q, and if this positively charged particle enters an electric field E, then it will experience a force. So here in this diagram, we have a charge Q of mass m, and it enters the electric field, say with a velocity v, in the direction OX, and this charge will experience a force in the direction of the electric field, which is in the OY direction, and that force is given as QE. And since this charge experiences a force in the OY direction, as it enters the electric field, it will be accelerated in the OY direction, and that acceleration is given as AY is equal to QE divided by M. And the distance in which this charge particle covered along the OY direction is given by the equations of motion, by using the equations of motion. And that distance is given as y is equal to uyt plus half ayt square. All these are along the OY direction. So here uy is the initial velocity along the OY direction, and since the initial velocity is along the OX direction, the initial velocity along the OY direction is 0. So here uy is equal to 0, and you have t then plus half ayt square. Now this t is the time in which the charged particle spends inside the electric field. And putting uy equal to 0, we have y to be equal to 0t plus half, and ay is equal to qe by m t square. So here your y will be equal to half QEM divided by t square. Now we'll have to eliminate this t, since we know that the distance covered, okay, from the diagram, the distance covered along the OX direction is given as x, and since v is the velocity in the x direction, the OX direction, from the definition of velocity is equal to distance or divided by time. Here the speed v in magnitude, the speed v is given as distance divided by the time. So hence the time t is equal to x divided by v. So putting the value of this t, we have y to be equal to half qe divided by m, and we have x squared divided by v squared. Now remember, this v is constant since there's no acceleration along the OX direction. The velocity or the speed is constant. Remember, acceleration means the change in the velocity or change in the magnitude of velocity, which is the speed. Since it is moving with a constant velocity along the OX direction, this v is constant. So hence we have y to be equal to qe divided by 2mv square, and all these are constant. Then we have x squared. So this equation is the equation of a parabola. Hence, if your charge is moving inside an electric field, it will move in a parabolic path. So now we'll see what will happen if a charge moves inside a magnetic field. We know that inside an electric field, if a charge moves inside an electric field, then it will move in a parabolic path. Now let us consider a charge q, and this charge q, it moves inside a magnetic field B with a velocity v in a direction making an angle theta with the direction of the field B. Then this charge inside this magnetic field will experience a force given as F is equal to qvb sine theta. Now this is just in magnitude. Q is the magnitude of the charge, v is the velocity by which it is moving, and b is the magnetic field, and theta is the angle between the direction of the charge and the direction of the magnetic field. Now in vector, this force is given as F vector is equal to Q V vector cross B vector. So it's given as the cross product of the velocity vector and the magnetic field vector. Now this force is called the magnetic Lorentz force, and since uh, it is a vector product of V and B, the direction of this force can also be found by using the right hand vector product rule. That is, you take the fingers in the direction of the velocity. In the diagram, you just take your fingers in the direction of the velocity, and as you cross this V cross B, you close your fingers towards B, and as you close your fingers towards B, you extend your thumb, and the thumb will give you the direction of the force. And in this case, the force is perpendicular to the plane containing this V and B, that is the uh, XZ plane, and is directed perpendicular to this plane, which means that it is directed along the Y axis. And remember, this force is called the magnetic Lorentz force. So that's what happens when a charge is moving inside a magnetic field. It experiences a force which is given as QV cross B, and the direction of that force can be found out by using the right hand vector product rule. Now we come to some special cases. Number one is that when a charged particle is at rest. Remember, in an electric field, if a charge is at rest in an electric field, it will still experience a force. But here, if the charge is at rest, which means that if the velocity is zero, then the force will be equal to Q0b sine theta, and that is equal to 0. So the force is equal to 0. Hence, when the charge is at rest, it will not experience any force. Then we have the second case. Now when the charge is moving parallel to B, means in the direction as that of the magnetic field, then here your angle theta, okay, which is the angle between the direction of the motion and the direction of the magnetic field, theta is equal to 0 degree or 180 degree. So if it moves in the direction of B, it is 0. If it moves in the opposite direction of B, then it is 180 degree. And in both cases, your sine of 0 or 180 is 0. Hence the force here also is 0. So therefore, if the charge moves in the direction parallel to that of the magnetic field, it will not experience any force. So here we have two cases when the charge does not experience any force. One is when it is at rest, the other is when it is moving parallel to the direction of the magnetic field. Then we come to the next case, that is number 3, when the charged particle moves perpendicular to the magnetic field B. Then in that case, the angle between the velocity vector and the magnetic field vector is 90 degree. Hence the force is equal to QVB sine 90, and sine 90 is equal to 1, which is the maximum value of sine. Hence we have force to be equal to QVB, and this force is the maximum force in which the charge can experience inside a magnetic field. So when a charge is moving perpendicular to the field, it will experience a maximum force. Now let us see what will be the direction of this force and what will be the path of the charged particle. So since this force is perpendicular to the velocity vector, it does not do any work. Okay, so therefore the magnitude of velocity remains constant. So what does this force do? It does not change the magnitude of velocity, but here this force will only bring about change only in the direction of the velocity. So, in other words, the force acts as a centripetal force, which makes the particle move in a circular path. So, this force, okay, the magnetic Lorentz force, it will make the charged particle move in a circular path. Okay, it acts as a centripetal force. What is a centripetal force? It is a force which makes any object move in a circular path. So this force, a magnetic Lorentz force, it acts as the centripetal force, and it makes this charge move in a circular path. So now we know that if a charge moves perpendicular to the magnetic field, then it experiences a maximum force, and the path in which the charge moves is a circular path. Now we come to another topic, that is a force on a current carrying conductor placed in a magnetic field. So we have learned what will happen to a charge when it is placed inside an electric field. We have also learned what will happen to the charge when it moves inside a magnetic field. Now we shall learn what will happen to a conductor carrying current uh, when it is placed inside a magnetic field. So here we have in the diagram, we consider a conductor of length L carrying current I, and this I is in the direction OI, and this conductor is placed inside a magnetic field which is in the direction OZ, and the angle between the direction of the current and the magnetic field is given as theta. And though it is you can see clearly that it is 90 degree, for simplicity we take this angle as theta. So this is valid for any angle, not just this 90 degree, but for any angle theta. Now we have learned that if a charge is placed, or if a charge moves in a magnetic field, then the charge will experience a magnetic Lorentz force. Now in this case, since current is the flow of electrons, okay, since the flow of electrons constitute current, so here we have an electron of magnitude of charge E, and this electron, since it is moving inside a conductor, or in other words, it will be drifted inside the conductor with a drift velocity Vd. And since the current is in the OY direction, the electron will be drifted in the OY dash direction, that is opposite to that of the current. So here a charge, namely an electron, it moves in a magnetic field, okay, with a velocity Vd. And since that charge moves inside a magnetic field, it will experience a magnetic Lorentz force given as F, small f, is equal to minus E Vd cross B. So this is the force experienced by each electron. Okay, so by one electron inside of the conductor. Now, if the conductor has n number of electrons, then the conductor, the whole conductor, will experience a force which is given as n times this small f vector. So hence this force experienced by the conductor, which is given by capital F vector, is equal to n f vector. Now n here uh, is equal to n into the volume of the conductor, where n, small n, is the electron density. Now you'll have to recall from chapter 3, we have defined this n, the electron density, as the number of electrons per unit volume. So this is where we get this formula from. So here n, capital N, is equal to NaL, and putting the value of this capital N in the above equation, we get F vector equal NaL. small f vector. And again, putting the value of this small f vector, we will get minus NALE VD cross B. So now we again can recall from chapter 3, electric current. The relation between the current and the drift velocity is given as I is equal to NAVDE. Now we multiply L in both sides, we'll get IL is equal to NALE VD. Now this IL, we have talked about this in the last lecture. This is known as the current element, and it is a vector quantity. It is in the direction of the flow of current. So if we take into account the direction of flow of current, the current element IL vector will be in the opposite direction of the drift velocity of the electrons. Hence your IL vector is equal to minus, because it is opposite to VD, so minus NALE VD. And if you look at the equation, minus NALE VD, this can be replaced by this IL vector. So in the equation F is equal to minus NALE VD cross B, we can replace that minus NALE VD by IL vector. Hence your F is equal to IL vector cross B. So this is the force experienced by a conductor of length L carrying current I when it is placed inside a magnetic field B. In magnitude, this is given as ILB sine theta. This is the cross product or a vector product. So in magnitude, we have F to be equal to ILB sine theta. And this angle theta is the angle between the direction of current and the magnetic field. So now we have these two cases. One is when theta is equal to 0 or 180 degree, which means that if you place the conductor in such a way that it is the direction of flow is in the direction of the field or opposite the direction of the field. That is, you place the conductor parallel to the direction of the field. So if you place conductor parallel to the direction of the field, then the force will be equal to ILB sine of 0 or 180, which is equal to 0. So if you place conductor parallel to the direction of the field, then it will not experience any force. Okay, so that is the case number 1. And the case number 2 is that if your theta is equal to 90 degree. So if theta is equal to 90 degree, then your force will be equal to ILB sine of 90, and sine of 90 is equal to 1, which is maximum. So here the force is equal to ILB, and this is the maximum force that a conductor carrying current I is placed inside a magnetic field. So we need to remember these formula. F, the force experienced by the conductor of length L placed in the magnetic field B. We will use this formula in the next topics. So now we come to the next topic, which is force between two parallel current carrying conductors. Now we have learned from the magnetic effects of current that a current carrying conductor will produce a magnetic field around it. So here we consider two conductors, X and Y, and conductor X is carrying current I1 and conductor Y is carrying current I2. So here the conductor X will produce a magnetic field around it. Similarly, the conductor Y also will produce a magnetic field around it. And these conductors, you can see in the diagram that they are placed parallel to each other at a distance r apart. So since the conductor X is producing a magnetic field around it, and that magnetic field is given as B1, okay, so the conductor Y will now be in inside the magnetic field produced by the conductor X. That is, the conductor Y will be inside the magnetic field B1. So similarly, even for this X also, the conductor Y will produce a magnetic field B2 around it, and the conductor X will be in the magnetic field produced by the conductor Y, which is B2. So X will be inside the magnetic field B2. Now let us consider first this conductor Y placed inside the magnetic field B1. Now the magnetic field at point P, okay, at a distance R from the conductor X, this can be found out by using Ampere's circuitous law, which we have learned earlier. And the magnetic field, due to Ampere's law, due to a straight current carrying conductor, is mu naught I divided by 2 pi r. So here the magnetic field at point P on the conductor Y, due to the current produced by the current I1, is B1 is equal to mu naught I1 divided by 2 pi r. So this is the magnetic field produced by the conductor X, and the conductor Y is placed in this magnetic field. And the field here is perpendicular to the plane of the paper and is directed inwards. So here B1, the direction of B1 is inwards, and it is perpendicular to the plane of the paper. So here we have a conductor, okay, Y placed in a magnetic field B1. And as we have learned earlier, if a conductor is placed inside a magnetic field, it will experience a force given as ILB sine theta. And in this case, the current is in a direction making an angle 90 degree with that of the magnetic field B1. Okay, so here I2 makes an angle 90 with the magnetic field B1. Hence, the theta is equal to 90. So the force, as we have learned earlier, is equal to maximum. Okay, so here your F is equal to I2 L B1. And here what we do is we take L to be equal to 1. That is, the force experienced by a unit length conductor Y will be given as Fy is equal to I2 B1. And putting the value of B1, we'll get I2 mu naught I1 divided by 2 pi r. And your Fy, force experienced by the conductor Y, is equal to mu naught by 2 pi I1 I2 divided by r. Now what will be the direction of this force? Again, here to find the direction, we'll have to write the force experienced by the conductor in a vector form. Okay, so in vector form it is IL cross B. So we have to take the direction of flow of current and the direction of the magnetic field. So here the direction of flow of current, okay, you have to use to know the direction of the force, we'll have to use the right hand vector product rule. So you put the fingers, all your fingers, in the direction of the flow of current I2. So the direction will be upwards. Then you close your fingers towards B. So IL cross B will be your fingers at in the direction of I2, then close it towards B. And as you close towards B, you extend the thumb. And as you extend the thumb will give the direction of the force. So here your Fy, okay, will be in the direction which is towards the conductor X as shown in the figure. So that is by using this right hand vector product rule. You point your fingers to the direction of current, close it towards B. That thumb, okay, the thumb extension will give the direction of the force. So similarly with the conductor X also, since it is placed inside the magnetic field B2 produced by the conductor Y, the conductor X also will experience a force. and the magnitude of the force is same as that of Fy. So here Fx is equal to mu naught by 2 pi I1 I2 divided by R. And the direction also again here, we put the your fingers in the direction of I1, then the B2 is outwards. Okay, B2 is outwards and perpendicular to the paper. So put your fingers along the direction of I1, then close it towards B2, and as you close it, you extend the thumb, and the thumb will give it the direction of the force Fx, which is towards the conductor Y. So here the force Fx is towards Y, the conductor Y, and the force Fy is towards the conductor X. Hence, these two parallel conductors carrying current, okay, in the same direction will attract one another. So in this case, you have two conductors carrying current in the same direction. They will attract one another. And what will happen if they carry a current in the opposite direction? If the current is in the opposite direction, then they will repel one another. So just like we have charges, positive repel, positive and negative. I mean positive they uh, repel, yes, and positive and negative they attract. So similarly here also, same direction of flow of current attract, different flow of current, opposite direction of current, the conductors will repel one another. And if you can recall from chapter 1, we have defined one coulomb, okay, by using the force experienced by the two charge. So here also we can define 1 ampere by using this force experienced by the two conductors. So to define the 1 ampere, what we do is we keep I1 to be equal to I2 to be equal to 1 ampere and R to be equal to 1 meter, so that the force per unit length experienced by the two conductors is equal to mu naught by 2 pi. And mu naught by 4 pi, we know that mu naught by 4 pi is equal to 10 to the power minus 7. So here mu naught by 2 pi will be equal to 2 times 10 to the power minus 7. Hence the force experienced per unit length is equal to 2 into 10 to the power minus 7 Newton per meter. Okay, so remember this force is the force per unit length because we have chosen L to be equal to 1. So thus 1 ampere, okay, can be defined as that current which when flowing through each of the two parallel conductors of infinite length and placed in free space at a distance of 1 meter from each other, uh, produces between them a force of 2 into 10 to the power minus 7 Newton per meter of their lengths. So that is the definition of 1 ampere.